Okay, the video for section 8.5, random variables, probability distribution, and expected value. So the video starts out with, we'll start with the definition of random variables and probability distributions, expected value, and fair games. The problems are really all expected value problems, so they're pretty much the same. Problems 1 or 2 in the book are pretty much straightforward calculations. The probabilities will be given to you. Most of the rest of the problems, all of these, for example, you have to calculate the probabilities like we did in the rest of chapter 8. Problems 11 through 13 and 17, 20, you should probably use complements. Excuse me. Problems 39 and 40 then are decision analysis problems. Okay, so definitions and calculations for problems 1 and 2. So we have a sample space filled with various outcomes. Then a random variable, and let's put a little bit of a red line underneath that. A random variable is a way of attaching a number, some number, to each outcome. And then you can set up a table that lists the outcomes and the random variable, the numbers that you get, and that's called a probability distribution. So, for example, suppose two people played a gambling game, person A and person B. So, in the game, a single die is rolled. If 1, 2, or 3 is rolled, player A wins $5. 4 or 5 is rolled, player A loses $3. And if a 6 is rolled, player A loses $6. So, the probability distribution is this. That's what a probability distribution is. The xi's are the numbers attached to the outcome. So in this example, they're the winnings or losings. So you could win $5, that's the plus 5. You could lose $3, that's the minus 3. Or you could lose $6, that's this minus 6. What's the probability? The PI's are the probabilities. So rolling a 1, 2, or 3, probability is a half. Rolling a 4 or 5, probability is 1/3. Rolling a 6, probability is 1/6. So, possible outcomes and probabilities. I usually use a more expanded probability distribution so that it sort of helps me understand what's going on a little bit better. What are my outcomes? I could roll a 1, 2, or 3, or I could roll a 4 or 5, or I could roll a 6, right, if you're rolling a 6-sided die. If I roll a 1, 2, or 3, if player A rolls a 1, 2, or 3, player A wins $5. A 4 or 5, you lose $3. A 6 loses $6, so minus 6. What's the probability of this? 1/2. Probability of this is 1/3, right? 2 out of 6. Probability of this is 1/6. So this part, these two rows, if you're doing Math Excel or if you're doing the book, that's what they would call a probability distribution. I like to explicitly include the outcome and a row down below here for the product. Right, and then the expectation value, that's the EV. So the first column is what's the outcome of rolling a 1, 2, or 3? You win $5, a probability of a half. Okay, now to calculate the expectation value, what do? In each column, you multiply the amount times the probability. So 5 times a half, that's 5 halves. Minus 3 times 1/3, that's minus 1. Minus 6 times 1/6, that's minus 1. Add these up, and that gives you the expectation value, which is, in this case, 1/2. So what is the expectation value? What does it measure? So 0.5, player A wins 50 cents on average on one roll of the die. Of course, on one roll of the die, you never win exactly 50 cents. You either win $5, or you lose $3, or you lose $6. So what does it mean that on average you win 50 cents? Well, multiple repetitions of the game. If they played this game 1,000 times, then player A would be expected to win a total of about $500, right? 50 cents each time he wins it. More or less. Maybe a little more, maybe a little less, right? So they never win exactly 50 cents on any roll of the die. But by playing 1,000 times, the $5 that you win, the $3 that you lose, the $6 that you lose, they balance out so that over 1,000 times, you'd probably win $500. So on average, if you won $500 in 1,000 games, you'd win, on average, 50 cents a game. So the expected value is how much you would win on average in one game. Think of it as if you played it a lot, this is what you'd win on average. So player A would definitely want to play this game because they win 50 cents on average. You play 1,000 rolls of the dice, you win $500. Player B, whoever player A's opponent is, they'd be losing 50 cents a game and would not want to play the game. So what's a fair game? A fair game is where the expectation value is 0, right? Over the long run, winning and losing balances out. Player A doesn't expect to win anything over the long run. Player B doesn't expect to win anything over the long run. And that sometimes is what makes gambling interesting, right? If you play a fair game, you might, over playing it 10 times, win all 10 times just by luck, and then you should quit. If you play a fair game long enough, you'd probably just win as much as you lose. Okay, so basic expectation value problems. And this is a lot of problems are essentially like this. So for example, 2 dice are rolled. If a 2, 3, 5, 7, or 11 shows up, right, total on the top of the dice, you win $12. If a 4, 6, 8, 10, or 12 shows up, you lose $10. And if a 9 shows up, you win $15. Should you play this game? Right? If you're going to play this gambling game, should you do it? And what's the expectation value? Well, we can put together a short probability distribution table for rolling 2 dice. Rolling 2 dice. What are your outcomes? You can have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. If you roll 2 dice and add up the number of dots on the top faces. How many ways are there to get a 2? Just one, rolling 2 dice. 2 ways to get a 3, 3 to get a 4, 4, 5, 6, and then back down, 5, 4, 3, 2, and there's only one way to roll a 12, 2 sixes. There are 36 possible outcomes. Okay, so rolling 2 dice, this is what we got. So what does our expectation value or probability distribution table look like? Well, we want our outcome. And what are the outcomes? You could roll 2, 3, 5, 7, or 11. You could roll 4, 6, 8, 10, 12, or you could roll a 9. How much do you win or lose? Well, 2, 3, 5, 7, 11, you win $12 plus 12. 4, 6, 8, 10, 12, you lose $10 minus 10. And a 9, you win 15. Great. So let's start putting some boxes around this. Zoink. What's the probability? And then the last line is the product. This is where we're going to do our calculations. What's the probability of rolling a 2, 3, 5, 7, or 11? Well, 1 plus 2, that's 3, plus another 4, that's 7, plus 6, that's 13, and 11, that's 15. So 15 out of 36. What about rolling a 4, 6, 8, 10, or 12? Well, 3 ways to roll a 4, plus 5 for 6, that's 8, plus another 5 for rolling an 8, that's 13, plus 3 for rolling a 10, that's 16, plus 1 for rolling a 12, that's 7. And then a 9, there's 4 out of 36 ways to roll a 9. So there's our probabilities. And they do add up to 1, right? 15 plus 17 is 32, plus another 4, that's 36 out of 36. Excellent. So multiply amount times probability, and you get 15 times 12 is 180 out of 36. 17 times minus 10 is minus 170 out of 36. And 15 times 4 is 60 out of 36. And what's our expectation value? Well, you just add all these up. So that's 180 minus 170. That's minus 10. It's plus 10, plus 60. So 70 out of 36. That's our expectation value, 70 divided by 36. So expectation value equals 70 over 36, which is 1.94. So what does that mean? That means that if you played this game, on average, you would win $1.94 every time you played. Pretty good deal. So if you played it for 10 times, you'd probably win about $19.40, maybe a little more, maybe a little less. If you played 100 times, you'd probably win around $194. So, should you play this game? Yes. You win a lot of money. The expectation value is $1.94. On average, that's how much you win each time you play the game. So, again, calculate an expectation value. What is your outcome? How much do you get for each outcome? What's the probability of that particular outcome? Multiply the amount times the probability downwards, then add across to get your expectation value. And again, these two rows, when you're doing Math Excel or when you're doing the book, that's what they call the probability distribution. Okay, example 2. 3 cards are drawn from a standard deck. You get $1 for each face card in the hand. How much should you lose if you get no face cards for the game to be even? Well, what are the possible outcomes? You're drawing 3 face cards. How many face cards could you have? You could have 0 face cards. You could have 1 face card. You could have 2 face cards. You could have 3 face cards. Okay, because you're only drawing 3 cards. What is the amount that you win each time? This is what the random variable technically is. Well, you get $1 for each face card in the hand. No face cards? Well, $1. 1 face card, you get $1. 2 face cards, you get $2. 3 face cards, you get $3. If there's no face cards, how much should you lose for the game to be even? Well, what does that mean? Well, we'll get to that in a second. What are the probabilities for this? Well, I don't know. We'll have to calculate that. It's a little bit tricky. And then the last line is the product. Multiply amount times probability. So let's make this little table. We'll put in some lines, outcomes, amounts, probability. And the last box, this is where our expected value goes. For the game to be, shouldn't be even, though. For the game to be fair. For a fair game, that means the expectation value has to be 0. Right? Nobody wins over the long run, nobody loses over the long run. And the question is, how much should you lose if you get no face cards? So what's the amount that should be here so that when you calculate the expectation value, you get 0? Okay. Well, that's not too bad. We just need to calculate all these probabilities. Probability of 0 face cards. What's that? Well, you want to draw 3 cards from the 40 that are not face cards and no cards from the 12 that are face cards, divided by the number of possible 3-card hands out of 52 cards. And if you calculate that, it's about 0.4471. That's the probability that you get no face cards at all. What's the probability of exactly 1 face card? Well, you have to draw 2 non-face cards and exactly 1 face card out of the 12 face cards, divided by C52.3. If you calculate that, that's 0.4235. Note that these two together, that's about 0.86. 86% of all 3-card hands have either 0 or 1 face card. Okay, what's the probability of getting 2 face cards? Well, that would be pick 1 out of 40 non-face cards, and then 2 out of 12 face cards, and divide by the number of total 3-card hands. That's 0.1195. And the probability of getting 3 face cards is pick 0 out of the 40 non-face cards, and then 3 out of the 12 face cards. And that turns out to be 0.0099. Okay. So now we can fill out our table. This is 0.1195, 0.0099. Great. So to calculate the expectation value, we multiply down 0.4471 times x, 0.4235 times 1 is just 0.4235. 0.1195 times 2 is 0.239. And 0.099 times 3 is 0.0297. At least that's what it looks like from my handwriting. Great. So add across and you should get 0. So this plus this plus this plus this should equal 0. If you actually do that, you should get 0.4471 x plus the other three numbers add up to 0.6992, 6922, and that should be 0. That's your expectation value. So how much should you lose for the game to be fair? Well, solve this equation for x, subtract this from both sides, divide by the 0.4471, and you get minus 1.5482. This is how much you should lose each time you get no face cards to balance out the winnings you get every time there is a face card, so that the game is even. So if you lost this much every time you got 0 face cards and picked up $1 for 1 face cards, 2 for 2 face cards, and 3 for 3 face cards, over a long period of time you'd probably come out even. Okay. Back to a black pen. So another version of this. The raffle sells 2,000 tickets for $1 each. There's one grand prize of $300, 2 second prizes of $200, and 5 third prizes of $100. So what's the expected value of one ticket? Well, again, start with your outcome. What can you get from this raffle? You could win the grand prize. Grand prize. You could win a second prize. You could win a third prize. Or, of course, you could win no prize at all. How much do you get? Well, if you get no prize at all, you lose $1, right? You buy a ticket for $1, you lose $1. If you get a third prize, well, you win $100, but you spent $1 to buy a ticket. So your net income would be plus 99, right? Plus $100 for winning, but minus $1 for your ticket. Likewise, for the second prize, it'd be plus 199, and for the grand prize, it'd be plus 299. $300 because you won, but $1 for your ticket. And what's your probabilities? Well, there's one grand prize, 2,000 tickets, so the probability of winning is 1 out of 2,000. What's the probability of getting a second prize? 2 out of 2,000. 2 out of 2,000. Probability of a third prize, 5 out of 2,000. What's the probability of not winning? Well, there's 8 winning tickets, so there must be 1992 out of 2,000 losing tickets. Great. So the last line is multiply these down. 299 times 1 over 2,000, that's 299 over 2,000. Two times 199, that's 396 over 2,000. 99 times 5 is 495. 495 out of 2,000, and then minus 1 times 1992 is minus 1 is minus 1992 over 2,000. So those are all products. To get the expectation value, you add those all up. And what do you get for that? 299 plus 396 plus 495 minus 1992 is minus 802 over 2,000. Okay, and if we divide that out, it's about minus 0.401. So what does that tell you? Well, a ticket is worth, the expected value of a ticket is minus 40 cents. Right? You expect if you bought a ticket, you'd lose about 40 cents. How much would you lose if you bought all 2,000 tickets? Well, if you bought all 2,000 tickets, you'd spend $2,000, but you'd get 300 plus 400, that's 700, plus, let's see, 400, 700, plus 3/3 prizes of 1,000, and you would be getting 3/3 prizes of 100. Sorry about that. So that would be 1,000. So you'd spend $2,000, but you get $1,000 back. So this should actually be 500. So I'm thinking I screwed up my numbers somewhere, because I'm thinking this should be 50 cents. Because if you bought all the tickets, right, how much money would you get? You'd win. Oh, there's 5 through. You'd lose about $800, right? And so that would be our $802. 5, 6, 7, 8. So the expectation value then, take the probability times the product, take the amount times the probability to get the product. 299, 199 times 2 is 390. Well, there's my problem. That's 398. So this 2 was bothering me. That's a 398. And then 5 is 495. So much better. Okay. Minus 800. So minus 0.4. Excellent. So you'd expect to lose 40 cents on one ticket. If you bought all 2,000 tickets, you would lose a total of $800 on this, because you would get $1,200 in prizes, 300 there, plus 400 from the second prizes, that's 700, plus 500 third prizes, that's 1,200, but you'd be out $2,000 on the ticket. So you lose $800 on 2,000 tickets. That means you're losing 40 cents on each ticket. And of course, raffles are always meant to have a negative expectation value for the people buying the ticket, because that's how the people running the raffle make their cut. Okay. Example 4. This is one of these complement problems. 5 cards are drawn at random from a deck. You win $10 if there's at least one face card in the deck. Otherwise, you lose $30 should you play this game. And what's the expectation value? Again, we set up our table. What are the outcomes? You could win or you could lose. What is the amount that you will win or lose? If you win $10. If you lose $30. Right. And what's the probability? And if you stop to think about it, right, for this game to balance out, for this to be a fair game, you should win about 3 times as often as you lose. Right? If you won 3 times as often as you lose, then you would lose $30 every time you lose, but in between losing, you would win 3 games and you'd win $30 back. So, should you play this game? Well, if the odds of getting a face card are about 3 times the odds of not getting a face card, then you should probably play. Otherwise, you probably shouldn't. So, what are the probabilities here? What's easier to calculate? Getting at least 1 face card or getting no face cards? And the probability is getting no face cards is easier because all that is picking 5 cards out of the 40 cards that are not face cards and then dividing by the number of 5-card hands. Again, at least 1 face card often means look at the complement. That might be easier to calculate. So the probability of 0 face cards is this, and that's 0.2532. So your probability of losing is 0.2532. What's the probability of winning? This equals probability of losing. Well, probability of winning is, of course, 1 minus probability of losing. And so 1 minus this is 0.7468. And so this is almost 3 times that. Your probability of winning is almost 3 times your probability of losing, but not quite. So we expect the expectation value here to be negative. So what's our products going to be? 10 times 0.7468, that's 7.468. Minus 30 times 0.2532, that's minus 7.596. So what's your expectation value? Add these two together, and that gives you minus 0.128. So on average, you lose about 13 cents a game, right? Because the penalty for losing is 3 times the prize for winning. The probability of winning is not quite 3 times the probability of losing. So you lose a little bit each game. Probably shouldn't play this. If you played, say, 100 times, you'd be out. What's that? $12.80. And maybe you just enjoy the game, and so maybe $12.80 is enough for that. Okay. Finally, decision analysis, problems 39 and 40. So, Carol owns bakery, and she's got a 5-year plan for a bakery. She wants to build an outlet store. And there are 2 sites. She analyzes foot traffic, jobs in the area. You know, are there jobs that are open early in the morning so that people are interested in buying donuts or something on the way home or on the way into work? Are they interested in buying a cake on the way home? In any case, at Site A, building will cost $250,000 and has a 60% chance of succeeding. If it succeeds, it'll bring profits. We actually don't want to make this $75,000. We'll say it brings in profits of $85,000 a year for 5 years, right? It's a 5-year plan. Building at Site B will cost $150,000 for the building, but that's got a 90% chance of succeeding, and if it succeeds, it'll bring in profits of $35,000 a year for 5 years. So where should she build? So what she's facing is that Site A is more expensive, has a less chance of succeeding, but if it succeeds, brings in a lot of money. On the other hand, Site B is less expensive to build, has a greater chance of succeeding, but doesn't bring in that much money. It brings in $50,000 a year less. So where should she build? Well, we'll do expectation values for the 2 sites. Site A, what are your outcomes at Site A? It could succeed, or it could fail. Right? What is the amount over 5 years if it succeeds at Site A? So if it succeeds at Site A, she'll bring in $175,000, right? Because that's $85,000 a year for 5 years. That's $425,000 minus the $250,000 that it costs her. Right, so 85,000 times 5 minus the 250,000. Yeah, 175,000. So that's how much you bring in. If it fails, right? If she builds and it fails, she's out the 250,000. So that's the penalty for failure. What's the probability of success? Oops, sorry. What are the probabilities? Well, the probability of success is 60%. What then is the probability of failing? Well, that's 40%. And you multiply those together. 175,000 times 60 is 105,000. Minus 250,000 times 0.4 is minus 100,000. So what's the expectation value? Add these two numbers together. It's $5,000. This is a tricky thing to estimate in this case because this isn't a game like the other ones were, right? This is saying, expectation value is saying, well, if you build at site A, on average, you'll make $5,000. But that sort of is, if you built at site A 100 times, then you'll make, a total of $500,000. But that's because some of them will fail and some of them won't. And in real life, you don't get a chance to build 100 times at site A. You just have to sort of, see what you can just build once. So, a little bit different from gambling games, but still it's useful information. You would, on average, come out ahead if you build at site A. But what about site B? What are your outcomes there? Well, you can succeed or you can fail. How much do you make if you succeed? Well, if you succeed, you make $35,000 a year for 5 years, and that is $175,000, but you have to lay out $150,000 to build. So over 5 years, if you succeed, you'll make $25,000. How much if you fail? You're out $150,000. What are your probabilities? Well, 90% success, 10% failure. Multiply those together. 0.9 times 25,000 is 24,500. Is that right? 22,500. I have a little difficulty with my handwriting there. So 22,500 minus 150,000 times 0.1, that's minus 15,000. So what's your expected value here? 22,500 minus 15,000, that's 7,500. So in both cases, site A and site B, you expect to make money overall, but not a whole lot. 5,000 here, 7,500 there. Where should you build? If you follow this analysis exactly, it says you should build at site B because the expected value is higher. On the other hand, the amount that you will actually make if you succeed is not very high. It's $25,000. If you succeed at site A, you make $175,000. So the expectation value can help you in your decisions when you're doing business type stuff, but it doesn't determine your decisions, right? If Carol is young and expanding her bakery, maybe she wants to take a risk that she makes that $175,000, even though there's only a 60% chance that she will make it. If she's older, heading towards retirement, maybe she doesn't want to risk losing the $250,000 at site A and will go for the almost sure thing of making just a little bit of money at site B. There's a lot of things that go into that. Expectation value can help you make a decision,